Electrolyte is a solution which conducts electricity. Basically, can take the electrons from one side to other side of a solution. Conditions for something to be electrolyte. First of all, it must be ionic, so it must contain ions. So sodium chloride is a compound that is ionic because it's a metal nonmetal, so we know it's an ionic compound. When we have ionic compound in aqueous solution, if it's soluble, those ions are moving around, and that is the second condition for a compound to be electrolyte. So first, it must contain ion. Second, those ions must be mobile. So if we have ions, but they are not moving around, like in solid sodium chloride, it will not be electrolyte. It's not going to conduct electricity. So we have electrolyte, and that's it's two types of electrolyte. One is a weak electrolyte, and one is a strong electrolyte. Is a weak electrolyte. Those are the electrolytes that they are reaching equilibrium. So that could be like a weak base, like ammonia. Weak base is a weak electrolyte. When it dissociates in water, it would generate ions, but it's going to generate just few ions or some ions. And since the number of ions that they are transporting electrons is limited, then number of electrons being transported is going to be limited. As a result, your solution is going to be weak electrolyte. A strong electrolyte, so that's one example, weak base or weak acid. Both of them are weak electrolyte. Strong acids, however, they are strong electrolytes. So HCl is a strong acid. If you see, look at here is a one arrow. That means it doesn't reach equilibrium. Dissociation is 100%. So when you have double arrow, that means dissociation is not 100%. Sometimes it's like 10%, 15%. So you get 15% ions. The rest would stay in the molecular form. But for a strong acid, it's going to dissociate 100%, and you get all of the ions produced in the dissociation. So you get a lot of ions being produced, and the electrolyte is classified as a strong electrolyte. A strong basis is another class of the strong electrolyte. So a strong base, like sodium hydroxide, so hydroxide of group 1A, like sodium hydroxide, potassium hydroxide, and soluble hydroxide of group 2A, like barium hydroxide, is going to give you a strong electrolyte. So it has to be a strong base or strong acid. A third class of the compounds that they are strong electrolyte, those are soluble ionic compounds, like NaCl is a soluble ionic compound. So if it dissolves like 100%, dissociates, and it gives lots of ions, and is going to conduct electricity stronger, so it would be a strong electrolyte. So this experiment, even if you were in the lab, since we are working with the conduct emitter and the chance for electric shots and other, we only have one of those electrolyte or conductor. We normally do this experiment as the demonstration. So I will demonstrate that for you. So these are questions from Prelab. It's just asking which ones are electrolytes, which ones are not electrolyte. Then we are going to perform the experiment to find out from the given items which ones are electrolytes, which ones are not electrolyte. Then when we are done with that part, I come back and I explain about titration. So we're going to finish one experiment first and then move to the second experiment. Please make sure to keep your data sheet open. So if you keep this open, then I'm going to ask you to tell me which solution I need to test next, because I want to stop sharing this document so you can actually see the video in the larger frame. You don't have to change the setting, so it would save it this way. Any questions before I close the document? Okay, perfect. So let me stop sharing the document. Now we have the experiments. We're going to start the experiment. Okay, so we have everybody now joining the experiment. Okay, so what we have here, let me, before I forget, let me plug in the charger. Okay, so we are going to test using the electrolyte property using conductometer. I'm going to plug in the conductometer also. I have to plug in and out. So, what is the first compound that you are going to test for electrolyte? The first one, deionized water. Is deionized water electrolyte or non-electrolyte? It's non-electrolyte. Could you tell me why it's non-electrolyte? So we have three groups. Perfect. We have three groups: non-electrolytes, strong electrolytes, and weak electrolytes. Non-electrolytes is either compounds that they are not mobile, substances that are not mobile, even though they have ions, but they cannot move around, and in like solid phase. Since it's not mobile, then it's not going to be electrolyte. Solids or ionic compounds that they are insoluble in water, they are non-electrolyte. Then molecular compounds. So water, because it's a molecular compound, is not soluble in. It doesn't generate ions, and since it doesn't generate ions, it's not electrolyte. And we are going to test it to see if it's electrolyte or not. So I don't know if you did follow me or not. I'm just going to repeat it one more time. Here is the conductometer. So after I plug in the conductometer to the power, if it does conduct electricity, then electrons from one pole is going to go to the other pole. And if that happens, so if the solution I have in this container, in the beaker, it is electrolytes, the light bulb is going to light up, and it gives like a bright light for strong electrolyte. It gives dim light for weak electrolyte, and it doesn't turn on if it's non-electrolyte. So we are going to test one at a time. So water, and that water has to be pure water or deionized water. That's what we're talking about. If it is a salt water, sea water, pool water, that's different story because it does have other ions in there. So pure water, the light bulb did not light up, so it's non-electrolyte, right? Record your observation and tell me what is the next compound that I should test. Next one, NaCl solid, NaCl. Okay, NaCl solid, electrolyte or non-electrolyte? It's going to not be non-electrolyte because it's not electrolyte because it's solid and it's not mobile. Okay, so it doesn't turn on the light bulb. As a result, it's non-electrolyte. So you can tell me what should I do next? Which compound should I test next? Sodium chloride in water. Okay. So I'm going to add sodium chloride to a beaker and add DI water. And test for the conductivity. With the conductometer, test the conductivity. Okay. Because it turns on the light bulb lights up and it's a bright light, it means that it is electrolyte and it is a strong electrolyte. Okay, next one. I'm going to wash these to make sure that it doesn't carry to the next. Glucose and water. What do you expect from glucose and water? Electrolyte, non-electrolyte? Okay, perfect. Non-electrolyte because is not because it's sugar, because it's molecular compound. Because it's molecular compound. So when we plug in, there is no light. So it doesn't turn on the light bulb. Non-electrolyte. Is the next one acetic acid? Acetic acid or ethanoic acid. Okay, glacial acetic acid. This is the strong, it's concentrated acetic acid. So glacial acetic acid or concentrated acetic acid, it doesn't contain any water. And in order for acid to be dissociated, it needs solvent, it needs water. So if it doesn't, we don't add water, it's not going to dissociate. Let me bring some paper towels. Right back. Okay. If we test the glacial acetic acid, okay, with glacial acetic acid, no light, so it's non-electrolyte for glacial acetic acid. Going to test with the dilute acetic acid. This is the acetic acid plus water. When you have the solvent is going to help. The solvent is going to affect, the solvent is going to dissociate the acetic acid into hydrogen ion and the acetate ion. So I don't know if you can see or not, but I will try to bring it closer. Do you see a dim light here? Yes, if you see a dim light, that means this is a weak electrolyte. So we have a weak electrolyte. That's why you see it like barely, right? That's why you see it barely. And I tried to make it dark so you could see. If I make it dark around it, you might be able to see it. Or if I put a black background, you might see it. Let me get a black background. Is it better? You see it better now, right? Okay. Good. So you have the 5% acid. Can you tell me what is next? Do you have the potassium phetalate next? Is that what you have? Yes? Okay. Potassium phetalate solid or liquid? The aqueous. Solid. What do you expect? Electrolyte or non-electrolyte? Non-electrolyte because it's solid. Very good. Next, is it potassium? Oh, is a potassium dihydrogen phosphate, sorry, in water? Add this to water? Yes? Okay. We're going to add some of these. And what do you expect? Is that compound soluble or not soluble in water? This compound is ionic and it is soluble. How do we know it's soluble? Because this compound contains elements from group 1A. Any compound that has elements from group 1A is going to be soluble. And because it's a metal and polyatomic ion, it's definitely ionic compound, so it's ionic and it is soluble, it dissolves, and a strong electrolyte. Okay, next one. Is that HCl? Yes, okay. HCl. What do you expect from HCl? Electrolyte or non-electrolyte? Aqueous HCl. Electrolyte, because HCl is a strong acid, and because it's a strong acid, it's going to be a strong electrolyte. It's going to be K plus and H2PO4. So basically dihydrogen phosphate. In the following steps, it can separate, but the major ions is the K plus and H2PO4. Sodium hydroxide is next one. Anything from group 1A, yes, any compound that contains sodium, it contains potassium, is going to be soluble in water. Like when they make soap is actually made of fatty acid and like sodium hydroxide or potassium hydroxide. So when they add that sodium or potassium component to fatty acid, it's going to make a compound that contains sodium, and because sodium is a group 1A, is going to be soluble. This is a sodium hydroxide. Sodium hydroxide is a strong base, as a result, a strong electrolyte. Is next one ammonium hydroxide? Yes, okay. Ammonium hydroxide is basically ammonia in water. Ammonium hydroxide is a weak base, is not strong base, so weak base. Going to test this. Most likely it's going to be deemed light, but let's try. Okay, it has a high concentration. It's a 3 molar. It's electrolyte. It's electrolyte. Ammonium hydroxide is a weaker base compared to the sodium hydroxide. I'm just going to try to see the strength to see how which one is more bright. Okay, going to see which one is more bright. Just compare it one more time. This is the sodium hydroxide I'm putting back. We already have the data. So this is the sodium hydroxide. And if I bring the ammonium hydroxide, just want to compare the brightness of the light. It is dimmer, right? It's dimmer. It's less than the sodium hydroxide. So this is a dim light. So weak electrolyte. So when you compare it, the light seems bright, but when you compare it to sodium hydroxide, it's much less. It's a dim light. And what is next? And alcohol. Okay, ethanol. Ethanol is going to be non-electrolyte or electrolyte? What do you expect from ethanol? Ethanol is a molecular compound, and that's why it's expected to be non-electrolyte, but we have to test it. So if you hear somewhere else also, so you have the proof that yes, we tested and it's not electrolyte. What is the next one? Is that ammonium acetate? Next one is ammonium acetate. NH4. Okay. Ammonium acetate. Ammonium acetate, even though it's coming from ammonia, but in form of ammonium acetate, you bring two polyatomic together. Ammonium acetate is two polyatomic together. So when you bring two polyatomic together, you're making ionic compound. So ionic compound is going to be a strong electrolyte. So ammonium acetate is not ammonia. It's ammonium and acetate, two polyatomic ion. With the two polyatomic ion is going to give you a strong electrolyte because it's an ionic compound. It's not a weak base anymore. Is the strong electrolyte. So ammonium acetate, you have two polyatomic ion together. It looks like just a metal non-metal or metal with polyatomic ion. Okay, next one, sodium sulfate. Right, sodium sulfate. Sodium sulfate, is it soluble or not soluble in water? Sodium sulfate is soluble because it has sodium and a strong electrolyte because it's ionic. Ionic, soluble, a strong electrolyte. Next, or probably the last one, is going to be H2SO4, right? H2SO4 or no? We're done? Okay, done. Why do we have H2SO4 here then? Perfect. Any questions about electrolyte, non-electrolyte? We already test for sodium sulfate, yes. NH3 is weak, but it depends on if it's NH3 in water, that gives you NH4OH, or if it's NH3 with another polyatomic ion. NH3 with acetate ion. NH3 with acetate ion is actually give ionic compound. So it's ammonium acetate. That is ammonium acetate. That's not NH3. It's an ionic compound and is soluble in water. Anything that contains ammonium ion is also soluble. So it's going to be a strong electrolyte. So that is a strong electrolyte. That is called ammonium acetate and is a strong electrolyte. NH4C2H3. Yes. Okay. We are done with this part of the experiment. So I'm going to find the experiment 12 now for you. Coursework, experiment 12. Okay. Sorry, I was pulling the wrong file. Okay, acid-base titration. What is acid-base titration? Titration is a method, and for titration as a method, we are going to find concentration of unknown solution, unknown acid or unknown base. We know the name of the acid or base, we just don't know the concentration. And when we add enough, we are going to neutralize it. You use the titration method using a standard. What is a standard? A standard is another acid or base that concentration of that solution or the acid or base is known to us. So if the concentration is known to us, we would call that the standard. And if the concentration is not known to us, is unknown, that is called the unknown for us. So in this experiment, we are going to use, are we using sodium hydroxide as the, we're going to use a base. So the acid that we are using is vinegar, and the base that we are using is sodium hydroxide. We are going to fill up the burette with sodium hydroxide, and we are going to add 5 milliliters of vinegar into Erlenmeyer flask. The Erlenmeyer flask, so we are going to add the acid into Erlenmeyer flask, add some water, and titrate with sodium hydroxide. So what's going to happen? When we add enough sodium hydroxide to neutralize all the acid that we have in the flask, that we are going to reach to end point of the reaction. We are using a phenolphthalein as indicator, and indicators, what is indicator? Indicator is a weak acid or weak base, is an organic compound. What is unique about indicator is that they have different color in acidic solution than the basic solution. So if we add phenolphthalein to vinegar, which is acidic solution, it's going to be colorless. It doesn't have any color. As soon as we add enough base to neutralize all the acid, in a neutral solution, phenolphthalein is going to be light pink color. If we add extra sodium hydroxide, it's going to change to dark pink or purple color. So we are going to add enough sodium hydroxide until we reach that light pink color. That means it's neutral. It means we have added enough base to neutralize all the acid. So that point, if we pick the indicator properly, it can correspond to equivalence point also, which means number of moles of acid equals number of moles of base. So end point is the color change of indicator, but equivalence point is the point that number of moles of acid equals number of moles of base. If the number of moles of acid equals the number of moles of base, then we can calculate concentration. So if we have molarity for the acid, volume for acid, if we have volume for base, we can calculate molarity for base. If we have molarity for base, volume for base, volume for acid, then we can calculate molarity for acid also. So this is a one equation with 4 variables. If we have any 3 of these, the last one can be calculated. So it's just like a cross multiplying, or you divide both sides by the numbers that are known to the side that is known. The equation we used last class was dilution. It was very similar to this, but that is the number of moles of dilute solution equal to number of moles of concentrated solution. This equation is for number of moles of acid equals number of moles of base. Now, is this equation like it works for everything? Maybe not, because it is not always simple. It's not like a 1-to-1 ratio, number of moles. It requires like a balanced equation. I didn't write the procedure, but it's not included, or for 1033, that's what we want you to just concentrate on. For this chemical reaction, the mole ratio, when you balance the equation, is going to be 1-to-1. That means it takes 1 mole of sodium hydroxide to neutralize 1 mole of acetic acid, which is the acid from the vinegar. So mole of the hydroxide with the mole of H plus from the acid is equal. So we use this equation of MA times VA equals MB times VB, and we solve the equation for concentration of the acid. This paragraph, it simplifies. If you have the concentration for the acid, how can you find the percentage of the acetic acid in vinegar? So the simplified version of it, which you have in the worksheet, when it tells you multiply the molarity by 6, is not a magic number. Is the relationship between the molarity and the percentage that is coming from molar mass of acetic acid, volume of the solution to calculate the molarity. So make sure you read these 3 lines before you assume that 6 is going to be always the same. So every time you have molarity, if you multiply by 6, you will get the percentage. It's not a universal formula. This formula is only specific for acetic acid, so it's not for all acids. Let me look at your questions, and then I'm going to go ahead and get help from you to get the procedure done. 1 mole of NaOH is not the 60 gram. 1 mole of acetic acid is the 60 gram. So basically what it's saying that number of moles of NaOH equals number of moles of acetic acid. So you take the same number of moles for acetic acid as you have for number of moles of sodium hydroxide. Because when you do titration, you reach equivalence point. When the color change happens, that means you have your number of moles of acid equals the number of moles of base. So if you have moles of acid, you would take the same number, you call it number of moles of base because of the equivalence point, and vice versa. So the sodium hydroxide, that solution that we have today, we are going to use this concentration because it's used as the standard solution. Volume is going to be determined using the burette. I'm not sure if this is the first time we are using burette, but we are using the burette to transfer the base into the flask using the burette. So when we read number, initially, that is not the volume of the liquid, because when it's filled up, it's going to read like 0. That's not the volume. For burette, we have the burette reading, basically. So it's the level of the liquid that we have in the burette. So if it's 0.00, that means it's filled up to the 0. And then when you open the stopcock and you transfer some of the liquid into the flask until you see the color change. Let's say if it comes down by 15, exactly 15, then the reading of the burette then is going to be 15.00, and the difference is how much liquid was transferred into the flask. So that is the volume of sodium hydroxide being used, and that's what we are using for our calculation in the data sheet. Okay. Questions? Any questions for me? If you don't have questions, let's look at the procedure. We are going to take a graduate cylinder, use 5 milliliters of vinegar in 200 milliliters of flask. And would you give me the procedure if I just use if I stop sharing this document? Okay. Going to stop sharing the document, go back to video. Thank you. Okay. First, I'm taking a 10 ml graduate cylinder to bring 5 milliliters of vinegar and place it into the flask. I'm just going around to fume hood to get that, and I'll be right back. Okay. Here's the vinegar. We're going to measure the 5 milliliters using graduate cylinder, and we place that into Erlenmeyer flask. We add 25 milliliters of water. Thank you. So we take ionized water and we use a 100 ml graduate cylinder to measure 25 milliliters of the DI water. Okay. And we are adding few drops of phenol phthalate. See, phenol phthalate with the solution is colorless. So after we add the base, when we add enough base, it would change to pink color. Now, I need to fill up the burette with 0.1 molar sodium hydroxide. So I'm going to get the sodium hydroxide, bring it to fill up the burette. We want to make sure to wash the burette first with water. So we add about 5 milliliters of water. We wash the burette like make sure that inside the burette is washed with water to make sure it's clean. Then add about 5 milliliters of sodium hydroxide solution, about 5 milliliters, to wash the burette. And discard. This is making sure that if there is any water in the burette, it's not going to make the solution that we are using our standard. It's not going to change the concentration of the standard. Then I fill up the burette up to 0 and a little bit higher than 0. Depends on your height. If you're really tall, you can leave it on the stand and just use it there. For me, it was easier to bring it down to read the number, because when you are reading the number, it actually, the level of the liquid should be at your eye level to make sure that you have accurate reading of the burette. Okay, so I filled up the burette with sodium hydroxide and adjusted to 0. Going to place the flask and add a piece of white paper underneath the flask. It allows me to see the color change better. Going to clear area, and you haven't had any screenshot. You could take a screenshot of this. So we add sodium hydroxide to vinegar. And I don't know if you can see or not. Let me show you. Is the pink color appears in the center and disappears, you see? That means we know that is working. We have added the phenolphthalein or indicator, but since it's not neutralized yet, it doesn't, the pink color doesn't stay. It appears and then it disappears. And the life of pink color is getting longer, so it stays there for a longer time. I just wanted to you see that pink color appears and disappears, but the proper technique for this is as you are slowly adding the standard or the base, you should actually mix the acid solution in the flask to make sure that is even distribution, or every molecule of the acid is being, or every unit of the acid is being neutralized. So you don't have only the center acid in the center being neutralized. Okay, the longer the life of the pink color gets, means that I'm getting closer to the endpoint of reaction. And if I'm getting closer to endpoint of reaction, I have to add 1 drop at the time to make sure that I'm not getting dark pink or purple color for this. When it's a light color, light pink color, I should stop. And that should happen with like 1, adding like last drop or the first drop that causes the pink color. Okay, see the pink color that appears is staying. Okay. Now the color change should stay for like 20, it should be stable for like 20 seconds. If it goes away right away, that means we have to add one more drop, but since it stayed for 10 seconds already, we're going to just wait for 20 seconds and read the volume. So initial reading for the volume was 0, 0. The final reading here is 42 point 42.30. So the initial volume was 0.00. And the final was 42.30. Thank you. Okay. Perfect. Okay. Question. This is the volume? Yes. So that would be the volume. Because you're subtracting 0 from that number, it stays as 42.30. So 42.30 minus 0, it gives you the 42.30 that is used as the volume of sodium hydroxide. Molarity for sodium hydroxide was 0.1. Volume for vinegar was 5.0. I use actually 10 milliliter graduate cylinder, so 2 decimal places, 5.00. And you find the molarity for acetic acid. Unit to the volume would be milliliter. Yes. Milliliter. It's going to cancel from both sides because it's milliliter on both sides. If you are not using the equation that volume appears on both sides, for number of moles, you should actually use liter instead of milliliters because you calculate the number of moles instead of millimoles. But since the units cancel from each side, you can use the milliliter. You don't have to do any conversions. Okay. Was it 1 or 2 trials? So it looks like it's asking for 1 trial of the perfect. Okay. Any questions? And your exam is next week, right? Next week sometime? Wednesday? Okay. So that's good. It gives me time to grade all your pre-lab questions and return it to you before the test. Okay, any questions for this experiment about electrolyte or titration? Where it tells you like a 0.1 times A divided by 5 is actually giving you the formula how to calculate to find the molarity of the acetic acid. So basically you're just getting the number that you have for A which is the 42.30 minus 0.00. And then you subtract that, whatever you find for line A, you use it for line B. And then what you find in line B, you're using that in line C. So you just follow the instruction that is given there. Okay, it's simplified. Not that I am, it's not my favorite, but at the same time, it helps you because when the lecture is behind the lab, then it's going to help you because at least you know what to do. You're not getting frustrated unless the titration like is already covered in lecture before you take the lab. For me, I usually ask the students to figure out actually, but it's perfect for situations that you don't have the lecture covered yet. Okay. Okay, any other questions for me? If you don't have questions, I'm going to stop recording.